Look here. So up to here, there is water level. Okay, this is the surface of water. Here, P1, V1. Here, P1 is equal to PA. Here, there is an orifice. This at a depth H. Okay, from here, water splashes out. Here, P2, V2, A2. Okay. Now, by Bernoulli's theorem, at this point, water slowly come down. It's a streamline flow. There we can write P1 plus rho G H1 plus half rho V squared. Okay. V1 squared is equal to, at this point, flow. P2 plus rho G H2 plus half rho V2 squared. So here, in this case, P1 is equal to P2 is equal to. P1 is equal to P2 is equal to. V1 is negligibly small. V1 is very, very smaller than V2. And hence, V1 is neglected. So this is gone. That completely gone. Then what is remaining now? See this part. Okay. Rho GH1 minus rho GH2 is equal to, you can write what is remaining? GH1. GH1 minus GH2 is equal to V squared by 2. Isn't it? Then V squared is equal to 2 G, I'm taking commonly out, H1 minus H2. H1 means top is H2. This is H2. So H1 minus H2 will give you H in the formula. So here we get V squared is equal to 2GH, or V is equal to root of 2GH. So this is the velocity of efflux. Clear? 2 into G into H. This height you take, you will get velocity with which it comes out. Is it clear? This velocity is known as velocity of efflux. Any doubt?
So which height should we
No,
take?
sir.
What is that? What is the question?
So which height should we consider?
From top surface to orifice. H1 means from down to here. H2 means from down to orifice. So H1 minus H2 will give you this depth. Is it clear?
Okay, sir.
Yes, sir, it's clear.
Now, there is one theorem called Torricelli theorem. Torricelli theorem. Okay. Look, Torricelli theorem. It's very interesting. Look here. Same height, I'm dropping a stone. And until this height, when it is reaching, what will be its velocity at this height? Here height is h, right? H. So here potential energy is mgh. At this point, this potential energy will convert into kinetic energy. That is half mv squared. Then we can write half mv squared is equal to mgh. M cancel. V squared is equal to 2gh. And V is equal to root 2gh. You see? That means this water which is reaching here and having a velocity, a stone which is falling under gravity, both are having same effect. This is what Torricelli said. Is it clear?
Yes, sir.
So that topic over. Next heading, surface tension. Next topic, surface tension. Okay. Look here. Surface tension. I will send some this one YouTube examples in that. Then you will understand that. Surface tension means, you see, you take some this one copper frame. How can you take copper frame? Take a bottle and take a copper wire and wind it around it. Copper wire, just one wound, and that handle you twist it, take it out. Then you will get a frame like this made up of copper. You will get a frame. Okay, this end. You get a handle. So on the handle, you can hold it. Is it clear? Now what you have to do? Here you tie a loose string, very loose string you tie here. Okay, like this. Okay, you tie very loose string like this. Anyway, you can tie it like this. Now dip in soap solution. Now you can see a soap film will come and form completely over here. Soap film everywhere. Okay, there is a soap film. Now take a needle, sharp needle, and heat it and prick in the middle. See this point, you prick it. Then what happened? That film will break in the middle. Therefore, you can see this violet string, okay, which is marked violet, will go like this. And this will come like this. The reason this film pulling it upward, this film also pulling it upward. That means this film has a property of contracting. Clear? When they were beginning, they were all stretched to the center, just like a balloon. Stretched balloon, it will be stretched membrane. Is it clear? Now,
Sir,
other
I don't
example I'll tell you.
understand. Can you please re-explain?
You take a circular frame, okay? That you understood?
Yes, sir.
In that, tie two strings, loose strings you try, okay?
Okay.
Dip into soap solution.
Okay.
When you dip into soap solution, soap film will form here, right?
Yes, sir.
Take a needle and prick soap film between this thread, not outside, between this thread, okay?
Okay.
Now will the thread remain there itself?
No.
Thread will move like this.
Yes,
What is
sir.
the reason? This film, right? Film in this region now. Which region? Middle film is broken. Now there is film here, right? Glass film is here.
Yes, sir.
What of this film is there, right?
Yes.
That film will contract here. Contracting means it has to go to this side, right? Both sides. Isn't it?
Yes, sir.
Pulling the string to this shape.
Okay.
Then only area of the film will reduce, right?
Yes.
This is happening because, look here, molecules here are already closer, but because of this, soap film, that molecules are pulled apart. From center to here, molecules are far apart now. When you're breaking it, that molecules will go back to its closer place. So when the molecules go closer, that membrane will contract, isn't it?
Okay.
Do you follow?
Yes, sir.
So this contracting tendency is known as surface tension. Another example I'll tell you. Take a frame like this. And at the end, keep one small side like this, a movable side that is made of metal. It can move slowly, no friction. Maximum friction should be reduced here. Now this dip in soap solution. Will this string AB remain same there? That side AB will be there itself?
No.
What will happen to AB now?
Contract.
That AB will move slowly, it will move to CD. Why this side is moving? Because now film, when this film is there, molecules are connecting there, right? Year to year, there are molecules, isn't it?
Yes, sir.
Yeah. Now these molecules are far apart. When you're doing a work, you're doing a work. You're an external agent. You're pulling that side AB away from that, isn't it? So you are doing work. So you are spreading the molecule apart, isn't it?
Yes, sir.
So molecules has a force in between them. When you pull apart, force will develop between the molecules.
Okay, sir.
Now here you are doing a work opposite to that intermolecular force. Then between these molecules, some potential energy will develop, isn't it? Like a spring stretching it is, isn't it?
Yes, sir.
So there is a potential energy on this membrane. That is called surface energy.
I understand, sir.
Now just keep it. You can see this side is moving. And finally, that will come and reach here. How much closer they can come? That means this frame membrane has a tendency to contract. It's called contracting tendency of film. Is it clear?
Clear. Yes, sir.
This is called surface tension.
Okay, sir. It's clear.
And this property is because of intermolecular force of attraction. Any doubt?
No, sir.
Oh. Now I will send you some experiments on surface tension video. Then you see that. Compulsory you must see. In this type of classes, you should get more idea from YouTube. Write down now. The free surface of a liquid. The free surface of a liquid. Heading surface tension.
So you give the notes here.
Sir, but it's written in the notes.
Oh, okay. Sorry. Notes already you have with you. So I will just read it out, read the note. Okay. If you don't understand any statement, you ask me. The free surface of a liquid behave like a stretched membrane, having its natural tendency to contract, to have the smallest possible area. Because a spring, when you stretch a spring, it has always a tendency to come closer. Because when you stretch, there's energy stored in it. When energy is stored, that system is unstable. So that system always having a tendency to release the energy and come back to its initial state. So you can see that area reducing, right? That size is reducing. Then it becomes stable equilibrium. Same thing as stretched spring has a tendency to be always contracting, so that molecules will come back to its original position, so that energy will be minimized, so that it can attain equilibrium. Clear? That's the first statement. Smallest possible area. This is because of surface tension. Is it clear? Now, how surface tension is defined?
Sir, this surface tension is also there in chemistry, and what is the difference between these two?
Same surface tension. Same thing. Now, surface tension, how can we define? Suppose this board is a water surface. On that water surface, I'm just marking a small place like this. See, this is water in a beaker of water. Think from top, when you look, water will be like this water surface. There you imagine, just imagine, we cannot draw a line on the water surface. Imagine a line of length L. Now we know everywhere molecules are there in water surface. So let us think of molecules of this side. See, molecules here and molecules here. There are molecules everywhere equally spread. Now this molecules are being pulled this side by this side. Here also molecules are having contracting tendency. Everywhere molecules are trying to contract, isn't it? Like this. Isn't it? So this force acting on a length L. Okay. So if we imagine a line, this molecules in this side pulling this molecule this side. Here the molecules also pulling this side, but it comes in equilibrium. That it's not moving that molecules in the middle on the line. But force acting per unit length on that line. So we can say it's a tangential force. It is happening on the surface between the molecules. Clear? That means if this is the top view, this one. From side, if you look, molecule here, molecule here, molecule. The line is here. So molecule will be attracted here, molecule will be attracted here. So this is along the surface. So we can say surface tension is the tangential force, which is acting perpendicular to the imaginary line. Which is acting perpendicular to the imaginary line per unit length. So we can say surface tension is defined as F by L Newton per meter. Okay. You understood? Did you understand?
Yes,
so inside the beaker, this surface tension will not be there. Only on the surface it will be there. Now you may think, why this side? Will it act this side? On this, see, between glass and water, there is a contracting tendency here also, everywhere. But the thing is, adhesion means attraction between two type of molecule. Cohesion means attraction between same type of molecule. So here adhesion between water molecule and glass is very high. That's what this is not coming back. But you go to moon, for example, or there is no gravity. Break this glass. then you can see this will form a sphere. Because why? From sides, no force acting. But on the surface of the earth, this water drop, when you're placing here, glass molecules are attracting these water molecules all around here. That's what that is spreading and forming like this everywhere. Otherwise, no need to go to space. Take some water and throw up. You can see water drops is forming because air cannot pull this molecule like glass. That's what they are forming drop in air. Clear? In a container when you are placing, so when all the forces are pulling from a part, this will become like this inside the glass. Otherwise, that is spherical shape. The reason this is the molecules on the surface. Okay, you can say, see, this molecule attract this one, this molecule pulling it this side. So this has the tendency to go inside. Similarly, this molecule will be attracted by this one here, this molecule attracting here. So this will go inside. This molecule is attracting here, this molecule attracting here. See, all the molecules having a tendency to go inside. So naturally that will form what? Spherical shape. Now force is acting between molecule on the surface so that it get contracting. Is it clear?
Yes, sir.
Yeah. So surface tension means force acting on the surface only. Okay, so this is the reason drops, rain become raindrops, we can say, because of surface tension. Okay, next, surface energy also I told you. Surface energy means when a membrane is formed, someone should have worked. It will not automatically form. That means I have to take a frame and dip into water and take it out. So I'm doing a work. During the process, my energy transferred between the molecule in the formation of that film. So that is developing between this molecule. So energy developing between the molecule is known as surface energy. Is it clear? Now
Yes,
relation between, next page, relation between surface energy and surface tension. Look here. This is a metal frame. Metal frame, okay? Here I'm keeping another metal frame, this side and this side. Just write it. This is a frame. Here I'm keeping another movable frame, movable side. Okay, so this is a movable side. This can move here. So here there is a handle for this. No need of a handle, just I'm showing this one. Okay. Here film, a water molecule will form if you're dipping it. This is a film. So this is A, B, C, D, this side. It has a tendency to get contracting here, right? It has a tendency to get contract. So force acting tangentially between this molecule. See, these are the molecule. Force acting tangentially between this molecule is F. That's called surface tension. Per unit length, F into L. L is the side. L is the side. So we can say S into L. This is the force acting on this frame. Because force acting per unit length is known as S, surface tension. Here L length is there. So force acting here is S into L. Any doubt?
No, sir.
Do you have any doubt in this?
No, sir.
Yeah. Now what I'm going to do, by exerting an equivalent opposite force by an external agent, this frame is moved. See this AB. Okay, AB, I'm moving to this point A1, B1. This is shifted here. That is delta X. Okay, so new area formed is dA, delta A. Delta A is L into delta X. New area formed. Any doubt?
No, sir.
Since I have done more work, now this region also energy formed. Now think from zero. When this frame was at coinciding with the CD, okay, suppose this frame is here, for example. If this frame is here, coinciding with the CD, Now no film form, no energy between them. But if I keep pulling this one here, see, I'm doing a work. Surface area increasing, molecules are going apart. So energy is developing between them. When I reach it here, already it has some energy, surface energy. Now again, I'm increasing that surface energy. Is it clear?
Yes, sir.
Yes, sir.
So that surface energy only I'm going to calculate. So we can say work done in displacing this delta x is force into delta x. So W is equal to forces SL. But it has two sides. For example, if film is like this, one side film will form here, other film will form this side. Right? Two side film will come, right? If one film is forming here, here also film will form, this side also film will form, right?
Yes,
Yes,
sir.
sir.
Then molecules will have a contracting tendency on this film surface and this film surface. So two sides we have to consider here. So that's what we are taking 2SR, 2SL. There's a total work done. Forces 2SL because multiplying by 2 because on either side of the frame film will form. Any doubt?
No, sir.
Now 2SL into delta x. L into delta x is change in area. So W is equal to 2S into L into delta x. Leave it like that. Okay. Delta x, this is equation number 1. Any doubt here?
No,
No,
sir.
sir.
Now surface energy means work done per change in area. Work done per change in area. So work done is 2SL delta x divided by change in area again 2L delta x 2 times. So this will cancel. W by delta A is equal to S. So we can say surface tension is numerically equal to surface energy. Energy is joule, surface tension is volts, but they are numerically equal. This is the proof. Any doubt?
No, sir.
Now a numerical I will tell you. A U-shaped wire is dipped in a soap solution. A U-shaped wire dipped in a soap solution. This is U-shaped wire. This textbook question. A U-shaped wire dipped in soap solution. And removed. That means here what happens? A film will form on this. Now this side, a thin film is formed between the wire and the light slider. This is a light slider we are discussing about. Slider means it can move up and down. Okay. So here a film is formed between light slider and the frame. Film is formed. So these are the molecules of that film. Weight of the slider now acting downward. Weight of the slider acting downward, that is mg. But slider does not fall because there is a equal and opposite force developing by the film along the surface. That is how much? F is equal to 2SL, same like before. Is it clear? So question is this: a U-shaped wire is dipped in a soap solution and removed. A thin film is formed between the wire and the light slider. Suppose weight of the slider is 1.5 into 10 to the power minus 2 Newton. It's given, which includes smaller weight of the slider. Weight we have added here. This includes this weight of the slider also added here. If the length of the slider is 30 centimeter, if this is 30 centimeter, find the surface tension of the liquid. So naturally we can equate here. 2SL is equal to mg. Then S is equal to mg by 2L. M is already given 1.5 into 10 to the power minus 2 into 2 into 30, 0.3 meter. From here, surface tension we can calculate. Any doubt? Any doubt in
No,
this?
sir.
Next
No,
one,
sir.
molecular theory of surface tension. Molecular theory. Suppose this is a beaker. Why this surface tension C is only on the surface? That's a question. This is a water surface. If you take a molecule here, it has a sphere of influence. That means it has an intermolecular force of attraction to all the sides. Molecule is a sphere. So all around there's a sphere of influence. It can attract other molecules. Clear? So we can say if this is A, a molecule from this side will attract here, here will attract. All the sides it's being attracted. So we can say this molecule A is under equilibrium. If I'm taking same molecules just below here, is the sphere of influence is like this. That means most of the molecule is downward, right? So there is a resultant force pulling it downward. When it is on the meniscus at C, half of the molecule down, half upward. This time what happened? Maximum downward force act. So this is having no force acting onto it. This is little force acting. This is the maximum downward force. Clear? So that is the reason I'm telling you on the surface only this downward pull or contracting tendency mostly seen. Here also you will see, but I told you because of water molecule are being strongly attracted by glass, that's what this side it's not coming. Instead of water, takes the mercury. Mercury will not be attracted by the glass. You can see a sphere is forming here because mercury will have cohesion. Attraction between the molecule is stronger than attraction between mercury and the glass. That's why it's forming droplet. Lotus leaf, you know, lotus flower leaves, you put some water, that forms sphere. Because that leaf, if you're taking water drop, will not be attracted by this.